for the last talk in the regular track today here. Should I start? Yeah. Okay, let's get started. We have only half an hour. Let's talk about functional programming with Python. No, this way. Okay, functional programming is nothing new, actually. It's one of the oldest programming paradigms. So Lisp has, if you look at those charts, says 1958 it came out, and Lisp has functional programming features. It's pretty much a functional programming language. But lately, in the last few years, functional programming made kind of a renaissance. It came back. You might know F# from Microsoft, Haskell, Erlang, all those languages. They are quite popular nowadays. And they're used quite a bit in different areas, like trading. People may not talk too much about it. A lot of areas where we have a lot of algorithms. Telecommunication, Erlang is one of the languages that are used there. So it's used in places. A few features of functional programming. I just grabbed a few features that I think are important. There might be some more. So everything is a function. If you have real functional programs, everything is a function. So usually in Python, so everything is an object. Now everything is a function. And you have what's called pure functions. So there are functions without side effects. That's one of the core things in functional programming. And you work a lot with immutable data structures. It's very different than what you used to. Usually, if you don't do functional programming, you use immutable data structures. And very often, you preserve the state in functions. So the concept of state is very different in functional programs. So you use functions to preserve state. And very often, you use recursion instead of loops, which is can be a very tricky thing if you use recursion and replace iterations. Few advantages. So if you write real functions programs, you have a few advantages. If you don't have side effects, you can make very robust programs. That's very important. Very often, if you do it right, those functional programs, they used to be much more small building blocks and much more modular. That's one thing. And if you do test-driven development, you write a lot of tests, you will naturally lean to this approach, writing smaller pieces, and those functional programs, if they're done right, they are better testable most of the time. And very often, they come from the mathematical background, very often they focus on algorithms. And functional programming is conceptually better suited for parallel or concurrent programming. A big thing, now everybody gets a lot of cores of the process, so you want to use them. So functional programming can be one solution to this problem, because you don't have to do a lot to make it work in parallel. For instance, like Erlang, you can have live updates of your running system. So some things are up for years and they get updates while they're running, because things are different in functional programming. It would be impossible if you use different kind of programming as you usually do in Python, for instance. But there are also a few disadvantages if you do functional programming. So functional programming is pretty different in many regards. If you see a fully functional program, like if you look at a Haskell program, it's very different. And as you used to, though it's difficult to find people that really know functional programming and use it right, if you use a functional programming language. And it's not actually used for all kinds of problems. For some kind of problems, it's very nice. And for some, it makes it harder. That's a problem. For instance, input-output is a side effect, so it doesn't really fit in this thing in functional programming. If you do input-output, you need some special kind of thing to get it working. Yeah? And the recursion, if you work with recursion, you see every first time you write a functional recursion, probably is wrong. You get something wrong. It's pretty difficult to write good programs with recursion instead of loops. And immutable data structures might be a performance problem. Depends sometimes if you have a functional program, the compiler's doing a lot about it. But if you use a language like Python, immutable data structures can be a big performance hit. Let's look at Python a little bit. Out of those functional features, there are a few in Python. So you can write functions in Python, and you can try to write pure functions. It doesn't really work. You will see in a minute why it's like this. You have other things. You have closures. Closures are helpful to keep state in functions, so you have a few of those things. Functions are objects, and you can also use decorators. There's a few things that help you to go in this direction, function-style programming. We have immutable data types. Yeah? Strings is one, tuples the other one. There's something what's called lazy evaluation. There's one of concept in many functional programming. They are lazy. They calculate things only when they're really needed, not before. Generators is a step in this direction. We have list comprehensions, and with Python 2.7 dictionary and set comprehensions. Then there are a few tools, func tools, a few libraries in the standard library, func tools, iter tools. We have lambda, map, and filter. So a few of those things are there that are actually have a functional programming background. Recursion is something that's not the best fit for Python. If you try to work with recursion with Python, it can be very slow and on top of it being difficult. That's a few features. And let's look at those features in a little more detail before we go to some examples. Actually, you can try to write functions without side effects. Would look like this. You have a function that takes data and returns a copy of data multiplied by 2. The problem, if this is a list, yeah, in the nested list, then you can have what's called the shallow copy problem. You only multiply the list itself, but not the references in the list. And then if you have a list in a list and somebody changes the list, it's changed. That's what I call the shallow copy problem. And also if somebody overloads the multiplication operator, a lot of things can happen that have a lot of side effects. A lot of things. You don't know what people are doing. So if data has operated multiply here, then a lot of things can happen. So there's no guarantee of pureness. So you have like a pure function by convention, but you cannot really enforce it with the current Python if you don't do anything special. There's no such thing like a pure function. You can try and say, I would like to have it act like a pure function, but there's no real way to enforce it. Side effects are very common. Very often you get a list and you append something to a list. It's a side effect. That's something you do a lot in Python. In Python, functional objects, which helps a lot to go into this functional style programming. I have a short example here. So I have just two very simple functions that just return 1 and 2, and you can just stick them in the dictionary and get in the dictionary and get it out. So those kind of things you can do, and this makes a lot of things possible. You can get a lot of elegant solutions, a lot of dynamics in there without just a little dictionary work, for instance, and some functions, because functions is not ordinary objects. As long as I don't call them, just stick them in here. They don't do anything special, but I can move them around the way I want them. So the everything is an object versus everything is a function thing can help you here. We have closures, so something like this is nested functions can act like this. You see I have an inner function here, and this inner function has access to this outer arc. And if you do this, you can return the functions. That's sometimes called a function factory. So you get a new function, and this function here, this 10, is bound to the outer arc. And if I call this inner function with 5 here, so this one is called this 5, 5 plus 10 is 15. And you see there's something what's called the closure. And then this closure you can index with 0, and then you look in the content, that's a 10. So this outer function stores state. And that's something you usually do in functional programming. Storing state in functions is a very common thing. So that's another building block you could use for functional style programming in Python. Then you have the functool modules, and this functool modules has only one thing in there in Python 2.7. It's called partial. And partial is very easy. You just define a function that takes the arguments a, b, c and returns them as a tuple here. That's it. And now I apply partial, and partial takes a function as the first argument in the 10 and fixes the a. The a is fixed to 10, and then if I call this function that returns, it only takes 2 arguments, and you see the a is fixed and only returns a b and c. That's what partial is doing. This is a very common concept. So if you look in Haskell, pretty much every function takes actually only one argument and does a partial to the next one. That's a very common thing in functional programming. Recursion, you can do recursion in Python if you do something like this. So replacing this loop, which is very straightforward to read, you just have a loop and just do something, you just add 1 plus 1 a loop. So the adding doesn't make any sense here actually, but the loop. And if you write the recursion, it takes much longer to scan and really read what it's doing. If you look at it, it looks much more complicated, and it takes you quite a while to understand, okay, if it's less than 0, less equals than 0, then return. And you have to make sure, if you only test for equals 0, you might be out of luck if somebody gives you a negative number here, then you will never return because you keep going, and this function is calling itself and getting more negative. So those kind of things happen if you work with recursions and don't think. Because it's very simple, it gets more complex. Those things happen all the time, and you get something going off. Python has a recursion limit of 1,000. You can increase it, and that's what I did. I checked how long it runs with 1,000. You see, and if I run it with a loop version, it takes 48 microseconds here, and here takes more than 10 times as long, factor 10. And then I try to bump up the recursion limit to 1,000,000, and this is stack fault on me. So this is something Python very rarely does it. So in IPython, so I don't know which one. But that tells you already that there's a problem, and recursion is usually not the way you solve problems in Python, unless you have like very recursive problems like nodes or something like this, where you need a few recursions. But so many recursions is usually not the way to go with Python. Lambda, it's in Python. Lambda gives you very simple anonymous functions. It's very simplified. You can only use expressions there, no statements. And actually, a few years ago, they talked about throwing it out of Python 3, but it made it through, and it's still there. And it's very easy for use for callbacks. You see, that's a function that takes a function with some arguments and calls this function here. And you can use Lambda. Lambda just takes, this is the argument, and this is a return value. That's it. That's all you can do. It's only a one line all the time. But they are not really necessary. You can always, they're not essential. You can always write a normal function, which has the advantage you give the function name, which serves documentation, and you can actually put a doc string in. So lambdas are not really necessary. Just to have to write a few more lines, you get there also. Okay, then we have list comprehension. So list comprehension is a very nice feature. It's actually, the term list comprehension comes from Haskell. They use it there. So obviously it's a functional thing. And before, it's still there in Python, we can use map. Map just say, okay, apply this function here to all these elements. Yeah, that's just, okay, multiply all the elements by 2. You can do this with list comprehension much easier nowadays, and usually it's a bit faster with list comprehensions, and just do the same thing with list comprehension. Another building block you can use, and also the same thing, filter is still there, but you can use list comprehensions with a condition here at the end, and you filter things out. Decorators is one, so it's an application of the closure thing. So decorators are a little bit advanced, but also they take advantage of this. Then decorator is actually just a function that takes a function and does something additional, returns a function. You just take a function here and return a new function, and in between I do something. And if I use this decorator here, then you see if I call it, it's just doing something in addition. That's something decorators do. You should use functional wraps to get everything right and nice. That's just a technical detail, but that's what decorators do. This has some functional style programming to it already. Immutable data types, Python has tuples, so you could work with tuples instead of lists. Yeah, it's very easy, just convert it to a tuple, no problem. The problem is it goes a little bit against how you usually work with Python. Lists you should use usually for lots of elements of the same kind of a list of file names, a list of numbers, things like this. And a tuple is usually for elements that have different meanings, like a name, last name, first name, age, things like this. That's what you would stuff in a tuple. And if you use a tuple, which is possible for a lot of, would go a little bit against the philosophy of Python. That's one thing that you might have here. Okay, you can use sets, you can freeze sets, which makes immutable data types, and it gives us the possibility to use it in dictionaries. The problem is, if you write a functional program, it can be very nice, but there are a few things that just don't really work. Input-output is one of them, and maybe for others. So you want to combine it. And that's what Python is good for. Python has this few functional features, and now when you write a program, you typically combine it with some other features. That's what I want to show you, some practical things what you can do. And you have to really choose the right tool for the task and decide, and try to get a feeling when the functional approach might be an advantage. So if you use a lot of recursion, then Python might not be the functional approach might not be the right tool for this kind of job you want to do. For instance, side effects. We still use classes here, so classes, but we still try to avoid side effects. That's one way of using side effects. So instead of going on and saying self something equals here in a method, I just do everything in it, and I call a function that's doing everything for me. This function tries to be without side effects, just returns something, and then I put it here. So it is a kind of a simple thing, but this simple thing can help you to maybe make your programs better readable. So if you ever use PyLint, it will always warn you if you initialize an attribute later, not in init. Here you initialize all them in init, but you don't want to write a gigantic init, so just use a function actually. A static method is nothing in a function, but since it belongs to the class, I call it static method. So there's maybe one use of a static method here. So set all attributes in init. So if you use PyLint, they will always nag you if you don't do, which is a good thing. And actually there's a use for static methods. And then you reduce the side effects. In Python, you will never get away with no side effects at all. But reducing the side effects might be a good thing already. So that's more the engineering approach. It won't be perfect, but good enough. There's another talk. Good enough is good enough. And at least it's better than having a lot of side effects, having just a few. And you still can use classes. So even if you use some of those functional programming methods, you can still use classes. And the inheritance, this inheritance is like if you do something like this, you see, now you don't even need to override init and use super, you just implement a new make attr1 in your child class, in your subclass, and then you don't have to, if you do something like this, if you do this attribute setting in steps like this, in smaller steps, you see the small thing, just everything is a small function here, then you don't need to call super, and you have other mains to get maybe some even more flexible. Depends on your application, so nothing's absolute here. You can freeze classes. So the immutable thing is a very big thing in the functional world. Everything is immutable, which can make things very difficult sometimes to program. But with Python, you can do something like this. You can freeze functions. Like what I'm doing here with this method read, it's just very simple. I just open a file and read it, and just in the traditional way, we see that you can do it shorter. I just go through the file and split the file into a tuple and append it to a tuple. So I get back a tuple of tuples and read it. And as soon as I want to convert it into tuple, it's immutable. Here it's a list. I can do a nice append. And just imagine you do more fancier things, which can be nice, because now you can append, you can grow the list until you know about how big it is, and in the end you convert it to a tuple. That's what I call freezing. You just convert the list to a tuple. That's actually all. And then you have a read-only version, and every time you will change it, it doesn't work. Python will throw an exception, you cannot change it. And then you see then you want to modify things, and that might be a problem. That's freezing. You can do this in one line, so instead of doing this, you can do it with a generator expression here. Just go through and generate a tuple of tuples and return it, and put it up there. And the same approach, I don't do it directly here. I put it in a function down here, and I could replace the read. So that's one of the things. So if you work a little bit more with immutable things, you will see in some places it can be useful. You could do it stepwise. So you can do this freezing and thawing. It depends how you need it. And it's not very difficult in Python. You just have to override a few special methods. Here, a get item and a set item. The get item just returns. I have a representation dictionary, and I have a flag frozen or not frozen. It depends if it's frozen or not frozen, so do different things. Returning always works with get item. Set item only works if it's not frozen. If it's frozen, I throw a key error. Like you cannot set things. And then you can just say freeze and unfreeze and do those things. And if you use it, then like here, the beginning is not frozen. I can set things. As soon as I can freeze it, I cannot set it anymore. It's a very simple thing, but it can be very, very useful. And then you can unfreeze it again if you want to go back to the mutable part, so you can change things again. And this can be very useful. So I work quite a bit with legacy code. So you get code, and you don't know really what's going on. Where the heck are they going to change this data structure? What's going on? So if you replace this data structure with this freezing, just add this freezing, and then you will see where people are going to change the data structure. The programmer tells you, don't change it, but you don't know. A lot of people worked on it. And that's one technique. So you will see if somebody's going to change it, that will be an exception. The other thing also, if you have a complex system and there's a lot of things going on, you might have periods you don't want to change things, and you use this freezing. That's one thing, because this immutable thing is a big thing in function. This is one key feature, because everything is immutable, makes a lot of things possible, and you should try maybe to freeze things and you can see what's going on. That's one practical application I see. Counter arguments. Immutable data structures can make things more difficult, some algorithms, but you can always thaw them, unfreeze things. And sometimes can be rather inefficient. One of the examples, Python strings are immutable, and you might see this kind of thing. If you do this a lot in the loop, nowadays in standard Python, that's pretty fast, but only it's optimized. If you try this in JSON or standard PyPy, so if you don't have a special version with a special compile option, that's very slow. So if you compare to using a list and in the end putting a list, if you do this a lot. So this can be quite overhead, and I talk orders of magnitude here, maybe several orders of magnitude, depending on the size of your data. So that might be a problem with immutable data structures, but they also can be have kind of advantages. Going back and forth might be a solution, and the Python makes it pretty easy to do this without a lot of interference with your program. Lazy evaluation is another thing you can do with Python. You generate only what you need, So in Python 3, we see this a lot. You see a lot of iterators all over the place. Yeah, and that's Python 2. You see I use xrange here. In Python 3, xrange became range. That's one of the signs there. So you can use this. And here, this one, for instance, you just generate one element at a time. And this one can be very, very big. It doesn't matter. If you used a normal range or list comprehension, then it would generate a big structure in memory, which takes time. You might not use. And if it's too big, you get a memory error. So laser evaluation is one of those things functional programmers use. You have it in Python. And there's a lot of tools. So if you have never used iter tools, I recommend to you use iter tools. It's full of very nice functions to work with iterators as they would be just normal lists. You can zip them. Yeah, you zip two iterables here. Just for here, I use 2 strings, but it could be iterators. And they don't generate the intermediate list of tuples, what normal zip is doing, but you get back another iterator. Just convert it to list here, you can see it. The same thing you can do slicing. The normal slicing operator you can do here with the slicing, so none means the colon, so you can slice an iterator. This is something very nice, because iterator can be very long, actually unlimited, and you can still work with it here. So that's one of those tools. Okay, I would like to show an example. How much time do I have? Maybe 5 minutes. I quickly go through this quick example. I just go forward. I have this example. I have a log file. Let's say an application is producing a log file looks like this, just simplified version. And now I want to use generators and generate some kind of workflow problem to solve. This is a log file, and then I have I need a few imports, and then I have a small function. The small function is doing nothing else, reading this log file line by line. Yeah, I just say, okay, while true, endless loop. I read the line. If there is no line, I wait a tenth of a second, and then I continue and yield the line. So that's what the generator is doing, is yield the line. So this one keeps going, overreads the line, and the pointer on the file stays there, over it's going to read the next line. That's the first thing. The next function is very simple. It's just filtering out. So, all right, small function doing very small things. I just go through all the lines in my iterator and filter out everything that has this pound sign at the beginning and just yield. If it's no pound sign, yield the line. Otherwise, I throw away the line. The next one is very, very simple again. Very simple loop. I just take this line, split it, and take the last one. So it's just assuming there can be something in front. Just takes the last one and convert it to an integer. That's all the thing is doing. And the next one is just a function now that just makes use out of this. I just use this iterator. So, okay, I use my first read forever. Then I use this filter, that filter also command, and get another. You see the thing? Now you could put in more and more of those filters, more and more of those steps, and move strings through. And then in the end, I just do this. I just write the loop for numbers here and print out things. And you see it at the screen printing. I just use this one here at the end to print, because I use a \r here, see, to print it in place. Then you see the sum all the time printing. And it's going to keep going. And you could plug in small filters. That's some of the approaches that works if you use generators. And then just run the thing. You could also use coroutines. Coroutines in Python are also a feature that come with generators. And let's say the log file is a bit more complicated. It has arrow levels. So it's a very simple kind of log file, has arrow levels. And now I want to treat each arrow level differently. And I just do the same thing. Now I write a coroutine. First, it's just a small wrapper that's just doing nothing else but calling next on my coroutine. So if you know about generators, it's just convenient thing. And then I do the same thing, very similar, but instead of yielding, I say send. Now I convert a direction. I send something. You see, I send a line to a target. I get a target, and I send something to this target. That's a very different thing. Yeah, but the rest is pretty much the same as we had. You just keep reading this file. And the filter is the same thing. The filter gets a target, goes through, and sends the result to a target. The rest is the same. And the next one, again, it's a target, and here I use yield to get the line. Yeah, always use this yield, and the same here. I use a yield to get the line from outside, and then I get the target. And I'm doing the splitting here, and then send this. And you see the target has different levels here. I use a level, and this level is a dictionary I use to do things. And then I write, for every level, I write a handler they all look the same here, but you imagine everything is different, so for every fatal and so on, I write a different function is doing something here. They look all the same in this case, I just go through, you see they all look the same. And the critical one, the error one, and so on, they all look the same, it just prints something else out. And then I stuff them in a dictionary, and at the end I can write something like this. You see, I can just say, okay, read forever, open file, filter comments, get number targets, and you have this kind of workflow. And if I want to have another step inside, I can just get another and another and another step. This is, for this type of problems, this kind of generators, which I would put in this functional programming thing, can make sense. They can make your program more difficult to debug. So, yeah, those things, everything you try it out, I encourage you to try it out, but things sometimes come as a surprise. Things might get more difficult to debug if you do those things. But they can be nice. The thing is running forever, and it doesn't matter how big the file is. You work with a file like if you would have the whole file in memory, but you only read one line at a time. So that's a nice thing about it. Okay, we had only a very short time. I want to try to give you a very quick introduction to functional programming. And Python offers a few features. Python is not a full functional programming language, but offers a few features, and you can use a few. And the nice thing is you can start with just a very small one and use more of them. It's not pure functional. There's no such thing like a pure function in Python. You can try to write a pure function by convention, but there can always be a side effect. You have to be aware of this. That's very important. So as long as you're aware of a problem, the problem is only half as big. And for some problems, the functional approach is very nice, for some it's not. So you have to try it out. And if you look at functional programming books, they always, of course, they select these ones that are very nice for functional programming. So algorithmic things. For some algorithmic things, functional programming can be very useful because very often you can use the mathematical formula nearly one-to-one in your code, and it works nicely. But there are a lot of other things than algorithmical things, then the functional approach might not be as good. And you can combine things with object-oriented and procedural style programming. And I would say if you stay Pythonic and be pragmatic, you switch and use the best one and try things out. That's the message I want to get across. And we still have 3 minutes for questions. For the last talk in the regular track today here. Should I start? Yeah. Okay, let's get started. We have only half an hour. Let's talk about functional programming with Python. No, this way. Okay, functional programming is nothing new, actually. It's one of the oldest programming paradigms. So Lisp has, if you look at those charts, says 1958 it came out, and Lisp has functional programming features. It's pretty much a functional programming language. But lately, in the last few years, functional programming made kind of a renaissance. It came back. You might know F# from Microsoft, Haskell, Erlang, all those languages. They are quite popular nowadays. And they're used quite a bit in different areas, like trading. People may not talk too much about it. A lot of areas where we have a lot of algorithms. Telecommunication, Erlang is one of the languages that are used there. So you can make very robust programs. That's very important. Very often, if you do it right, those functional programs, they used to be much more small building blocks and much more modular. That's one thing. And if you do test-driven development, you write a lot of tests, you will naturally lean to this approach, writing smaller pieces, and those functional programs, if they're done right, they are better testable most of the time. And very often, they come from the mathematical background. Very often, they focus on algorithms. And functional programming is conceptually better suited for parallel or concurrent programming. A big thing. Now everybody gets a lot of cores of the process, so you want to use them. The functional programming can be one solution to this problem because you don't have to do a lot to make it work in parallel. For instance, like Erlang, you can have live updates of your running system. So some things are up for years and they get updates. Write good programs with recursion instead of loops. And immutable data structures might be a performance problem. Depends sometimes if you have a functional program, the compiler's doing a lot about it. But if you use a language like Python, immutable data structures can be a big performance hit. Let's look at Python a little bit. Out of those functional features, there are a few in Python. So you can write functions in Python, and you can try to write pure functions. It doesn't really work. You will see in a minute why it's like this. You have other things. You have closures. Closures are helpful to keep state in functions. So you have a few of those things. Functions are objects, and you can also use decorators. There's a few things that help you to go in this direction, functional style programming. We have immutable data style types. Yeah? Strings is one, tuples the other one. There's something what's called lazy evaluation. There's one of concept in many functional programming. They're lazy. They calculate things only when they're really needed, not before. Generators are it's used in places. A few features of functional programming. I just grabbed a few features that I think are important. There might be some more. So everything is a function. If you have real functional programs, everything is a function. So usually in Python, so everything is an object. Now everything is a function. And you have what's called pure functions. So there are functions without side effects. That's one of the core things in functional programming. And you work a lot with immutable data structures. Very different than what you used to. Usually, if you don't do functional programming, you use immutable data structures. And very often you preserve the state in functions. So the concept of state is very different in functional programs. So you use functions to preserve state. And very often you use recursion instead of loops, which is can be a very tricky thing if you use recursion and replace iterations. Few advantages. So if you write real functions programs, you have a few advantages. If you don't have side effects while they're running, because things are different in functional programming, it would be impossible if you use different kind of programmers, as you usually do in Python, for instance. But there are also a few disadvantages if you do functional programming. So functional programming is pretty different in many regards. If you see a fully functional program, like if you look at a Haskell program, it's very different. And as you used to, though it's difficult to find people that really know functional programming and use it right, if you use a functional programming language. And it's not only used for all kinds of problems. For some kind of problems, it's very nice. And for some, it makes it harder. That's a problem. For instance, input-output is a side effect, so it doesn't really fit in this thing in functional programming. If you do input-output, you need some special kind of thing to get it working. Yeah? And the recursion, if you work with recursion, you see first time you write a function with recursion, probably is wrong. You get something wrong. It's pretty difficult to